Pluto's way will undoubtedly cause issues from the very beginning. Pluto's orbit intersects with that of another planet, Neptune. Pluto, the strange and small planet situated in the farthest corners of our solar system, has become a hotly debated topic in cosmology. Recent updates suggest a potential collision with Neptune, raising concerns among researchers and space enthusiasts. Renowned figures such as Neil deGrasse Tyson and Michio Kaku have expressed concerns regarding the potential consequences of this celestial encounter. But how did Pluto end up on a collision course with Neptune, and what could this cosmic conflict mean for Earth? Join us as we explore the details of how such an event could have occurred and why scientists are unsettled by this astronomical anomaly. Pluto, once celebrated as a full-fledged planet, underwent a dramatic reclassification as a dwarf planet, largely due to its erratic orbit. Despite this demotion, Pluto continues to captivate and ignite interest within the astronomical community. Recent warnings from prominent scientists such as Neil deGrasse Tyson and Michio Kaku suggest that Pluto's orbit could intersect with Neptune's, implying a potential risk of collision with serious implications for our planet. Pluto's journey around the Sun is extraordinary due to its unique characteristics. Its orbit is exceptionally long, taking a massive 248 years to complete. Since its discovery in 1930, Pluto has not yet finished a full revolution around the Sun. What makes Pluto even more intriguing is the highly elliptical shape of its orbit, in stark contrast to the nearly circular orbits of the major planets. Moreover, Pluto's orbit is tilted at an angle of 17 degrees relative to the ecliptic plane, resulting in a steeper incline compared to the paths of other planets. This combination of inclination and its elongated orbit adds complexity to its motion. A remarkable aspect of Pluto's orbit is its repeated intersection with Neptune's orbit. Every 248 years, Pluto's path brings it closer to the Sun than Neptune, defying expectations based on their relative positions in the solar system. Further investigation reveals that Pluto's orbit is far from a perfect circle. Instead, it follows an elliptical or oval path, meaning its distance from the Sun varies significantly throughout its orbit. At its closest point, Pluto comes within about 30 astronomical units of the Sun, but at its farthest, it stretches to over 49 astronomical units, nearly double Neptune's distance from the Sun. Additionally, Pluto's orbit is inclined relative to the orbits of other planets, adding another layer of complexity to its relationship with Neptune. This inclination plays a crucial role in how Pluto and Neptune interact. When their orbits overlap, their gravitational forces influence each other, gradually altering their trajectories. This dynamic between Pluto and Neptune highlights the interconnected nature of the solar system, with each planet exerting gravitational forces that affect the movements of others. Over the years, advancements in observational instruments have allowed astronomers to track Pluto's movement with greater precision. This has led to a better understanding of its orbit and its potential impact on the overall stability of the outer solar system. Although the likelihood of a direct collision between Pluto and Neptune remains low, the possibility is still under scrutiny. Ongoing monitoring continues as the potential consequences of such a collision could be dramatic. Despite Pluto's small size and distant location, it remains a subject of interest for scientists and space enthusiasts alike. A key question arises: why hasn't Pluto collided with Neptune already? The answer lies in the gravitational influence of other planets. Since Pluto's discovery, astronomers have been trying to understand its path. Unlike most planets, which maintain a consistent orbit along the ecliptic plane, Pluto's orbit stands out with its steep angle and elliptical shape. The mystery deepened when it became apparent that Pluto's orbit crosses Neptune's. Despite this apparent danger, Pluto's orbit remains remarkably stable, showcasing the intricate mechanics that govern space. Studying the interactions between Pluto, Neptune, and the Sun presents a significant challenge for astronomers. Predicting their movements requires a deep understanding of how they influence each other's trajectories. To tackle this challenge, scientists rely on concepts such as azimuth libration, scope libration, and VSOP von Sippel-Steeves and Kaplan isolation to solve this cosmic puzzle. Azimuth libration, for example, is essential in maintaining the stability of planetary orbits. When Pluto crosses Neptune's path, it remains at least 90 degrees away, preventing a direct collision. Scope libration ensures that when Pluto approaches Neptune or other massive planets, it is positioned above their path, reducing the likelihood of an impact. The VSOP oscillation, named after scientists von Sippel-Steeves and Kaplan, explains why Pluto's orbit appears unusual yet remains stable over time. Although space may seem chaotic, there are underlying patterns that help maintain order. These patterns prevent Pluto from colliding with Neptune or significantly altering its orbit. The concept of orbital chaos, which describes how a celestial body's trajectory is highly sensitive to its initial position, is clearly demonstrated by Pluto's orbit. Even small variations in Pluto's position or velocity can have significant effects over long periods. In the late 1980s, simulations revealed something fascinating. Despite the apparent stability of Pluto's orbit, it can still behave unpredictably. A tiny change in Pluto's starting point or velocity could lead to massive changes in its orbit over time. However, even with these uncertainties, Pluto's orbit remains stable for billions of years, suggesting that despite its irregular appearance, it follows an underlying order. The unpredictability of planetary orbits such as Pluto's makes it challenging to predict long-term changes with certainty. These models require highly accurate initial conditions, as even small errors in data can produce vastly different outcomes, making precise predictions incredibly difficult. Understanding Pluto's orbit is essential, particularly when considering the potential for a future collision with Neptune. This knowledge contributes to a broader understanding of how our solar system operates. Pluto's orbit serves as an example of how seemingly chaotic paths can ultimately reach a balance, guided by the forces of gravity and motion. We must continue to observe and study these celestial mechanics to gain a better understanding of our place in the universe. Pluto's orbit offers an ideal illustration of the unpredictable nature of space. Its oval shape leads to unusual encounters with Neptune. This irregular motion makes it difficult to predict the long-term dynamics of the system. However, gravitational forces play a critical role in keeping Pluto and Neptune in their respective orbits. Despite its irregularities, Pluto's relationship with Neptune remains a fascinating example of cosmic harmony. The gravitational interactions between the two bodies ensure that, although their orbits intersect, they do not collide. This delicate balance is maintained through a phenomenon called orbital resonance. Pluto and Neptune are locked in a 3:2 resonance, meaning that for every 3 orbits Neptune completes around the Sun, Pluto completes 2. This synchronized pattern prevents the two celestial bodies from coming dangerously close to each other. Orbital resonance is a common occurrence in our solar system and plays a vital role in maintaining stability among planets, moons, and other objects. Pluto's unique orbit also serves as a reminder of the dynamic and ever-changing nature of our solar system. While it may appear chaotic, the intricate gravitational dance between celestial bodies creates a system that is surprisingly stable over billions of years. However, even minor changes to this balance can have significant consequences. Scientists continue to monitor Pluto's orbit with advanced telescopes and computational models. These efforts aim to understand not only Pluto's behavior but also the potential ripple effects on the outer solar system. Such studies are critical as they help us prepare for any unexpected developments that could impact the broader cosmic environment. In the grand scheme of the universe, Pluto may be a small and distant dwarf planet, but its story provides valuable insights into the complex mechanics of celestial motion. Its interactions with Neptune, its tilted and elongated orbit, and its resilience in the face of gravitational forces all highlight the beauty and intricacy of the cosmos. As we delve deeper into the mysteries of our solar system, Pluto continues to inspire curiosity and wonder. Its journey reminds us that even the smallest objects can play a significant role in shaping the universe. The study of Pluto and its orbit is not just about understanding one planet. It's about uncovering the deeper truths of the celestial forces that govern our solar system and our place within it. Neptune, through its impacting gravity, a power that draws objects to each other, guarantees that, in spite of their converging orbits, the two bodies stay separated. More often than not, these interactions mirror the delicate balance of forces at work in space. The possibility of a collision between Pluto and Neptune, while unlikely, would be a monumental event with significant consequences. Such an event would radically alter our understanding of the solar system. Although space exploration has advanced considerably, Pluto's orbit serves as a reminder of the many uncertainties that still exist. Scientists continue to study Pluto's path to better understand how massive planets influence its motion. This knowledge is crucial for understanding the complex relationships between celestial bodies and how their movements can affect one another. Despite the unusual nature of Pluto's orbit, some of the world's leading scientists, like Neil deGrasse Tyson, have hypothesized that Pluto may one day collide with Neptune. Tyson, a prominent astrophysicist, sees Pluto's reclassification as a dwarf planet as a critical step in emphasizing the importance of continued exploration and study. He believes Pluto's peculiar orbit underscores how much there is still to learn about space and the forces at work within it. According to Tyson, the mysteries of space make studying it so captivating, and he encourages others to engage with the fascinating complexities of celestial mechanics. Tyson, along with other experts, is concerned about the potential dangers posed by Pluto's unusual path. If a collision between Pluto and Neptune were to occur, it could have catastrophic ramifications for our solar system. The release of energy from such an event would be immense, and the debris scattered throughout space could have far-reaching effects, potentially even impacting other planets and moons. Neptune itself would be affected, and its orbit could be altered, further complicating the dynamics of the outer solar system. Renowned theoretical physicist Michio Kaku, known for his work in string theory, also provides valuable insight into space exploration. Kaku believes studying phenomena like Pluto's orbit is essential for understanding the broader principles of celestial mechanics and theoretical physics. He suggests that exploring Pluto's interactions with Neptune can help scientists navigate future space missions more safely. Kaku also emphasizes the importance of understanding gravitational forces in the context of space exploration, as they have the potential to shape the future of how we explore distant worlds. Kaku's work in string theory, which seeks to explain the fundamental forces of the universe, aligns with his interest in Pluto's orbit. A collision between Pluto and Neptune could offer invaluable data that would enhance our understanding of gravity and the spacetime continuum, key areas in string theory. Although such an event would not directly impact Earth, it could provide a unique opportunity to study the behavior of fundamental forces under extreme conditions. As scientists continue to explore the depths of space, the unpredictability of planetary interactions becomes increasingly evident. The study of celestial dynamics, such as the intricate gravitational relationship between Pluto and Neptune, offers valuable insights into the fundamental laws of the universe. By continuing to monitor and study these phenomena, we come closer to comprehending the vast and intricate nature of the cosmos. The gravitational dance between Pluto and Neptune highlights how even distant planets can influence each other. These celestial bodies exert gravitational forces that, over long periods, can shape their orbits in subtle yet significant ways. While a direct collision remains improbable, the possibility cannot be entirely ruled out, leading to ongoing interest and observation from the astronomical community. Scientists believe that understanding these forces may one day enable them to predict and potentially mitigate the risks posed by such cosmic events. One fascinating aspect of planetary motion is how seemingly random or chaotic interactions can lead to stable, predictable patterns. This phenomenon is especially true in the case of Pluto, whose orbit might appear erratic but is governed by precise gravitational forces. These forces help prevent Pluto from colliding with Neptune, despite the apparent overlap in their paths. The delicate balance between the gravitational pull of various planets and Pluto's orbit keeps the dwarf planet on a steady yet complex course. Understanding this intricate relationship is vital for advancing our knowledge of the broader solar system. As scientists continue to study the unique characteristics of Pluto's orbit, they also look toward other areas of space exploration. The study of systems like the TRAPPIST-1 system, which contains multiple Earth-sized planets, helps astronomers understand how gravitational forces between planets can lead to orbital resonances and, in some cases, increase the likelihood of a planet's path becoming unstable. Though the TRAPPIST-1 system is not currently experiencing any collisions, scientists remain vigilant, tracking the movement of planets in these crowded environments to better understand the risks and how they might evolve over time. Meanwhile, astronomers are also focused on understanding the behavior of rogue planets, which wander through space without being bound to a star. Rogue planets present a unique challenge for astronomers, as their lack of a central star makes their movements difficult to track. These wandering celestial bodies can traverse vast distances, potentially crossing paths with other planetary systems. The gravitational forces they exert during these encounters could disrupt the orbits of nearby planets, moons, or even asteroids. Studying rogue planets and their interactions with other objects in space is critical to understanding the unpredictable nature of the universe. Additionally, researchers are exploring how interstellar phenomena, such as black holes or passing stars, might influence the dynamics of planetary systems like our own. For example, a passing star could disrupt the orbits of distant objects in the Kuiper belt, potentially sending them hurtling toward the inner solar system. Events like these could have significant consequences for planets, including Earth, and highlight the importance of ongoing observation and analysis. In recent years, advances in technology have allowed scientists to model complex gravitational interactions with greater precision. These simulations help researchers predict potential future scenarios, such as the long-term stability of the solar system or the likelihood of collisions between celestial bodies. By combining theoretical physics with observational data, scientists can gain deeper insights into the forces shaping our universe. As our understanding of space deepens, so does our ability to protect our planet from potential threats. The study of planetary motion, gravitational interactions, and cosmic phenomena is not only a scientific pursuit but also a practical endeavor aimed at safeguarding humanity's future. Efforts to monitor near-Earth objects, NEOs, and develop strategies to deflect or mitigate potential impacts are a direct result of this research. The collaboration between astronomers, physicists, and engineers continues to push the boundaries of what we know about the cosmos. Space missions such as those conducted by NASA, ESA, and other international organizations play a pivotal role in gathering data about distant worlds and their interactions. From the discovery of exoplanets to the detailed mapping of our solar system, these missions expand our understanding of the intricate web of gravitational forces that govern the universe. Looking ahead, the exploration of space will undoubtedly uncover new mysteries and challenges. The study of phenomena like Pluto's orbit, rogue planets, and interstellar interactions serves as a reminder of the vastness and complexity of the cosmos. By continuing to observe, analyze, and theorize, scientists aim to unlock the secrets of the universe and inspire future generations to reach for the stars.